When we say LLMs or model, we often use this word without really knowing what they mean. In this series of AI engineering, we'll start from very first principles or guiding principles. We'll build a strong fundamental model or an uber idea of what large language models actually are, where they live, and how a user's input flows through a real production system. We'll understand the inference server and how these transformers work internally, what attention really does, and why GPUs and CUDA are critical for making this system fast and scalable. And as we go deeper, we won't stop at just the theory. We'll explore how modern AI systems are built in production, including concepts like RAG, tool calling, vector databases, and how latency and batching are handled at a scale. I mean, you must have always been thinking how we are getting the response so quickly. I mean, why? How come it's so fast? I mean, you just give a prompt and you get the results quite fast, right? So, is there any magic happening behind, or is there any other engineering that we don't know? So, we'll also step into agentic AI, like understanding what AI agents really are, how they reason across steps, and how they use tools, and how you can design such workflows around them as a software engineer. By end of this playlist, you should be able to reason about LLMs the same way you reason about any backend architecture, understanding their components, trade-offs, real-world constraints end to end. I mean, instead of treating them as a black box. So if you want to go from being a user of AI to someone who truly understands and leverages it in their day-to-day work, so make sure you subscribe and follow along. This will be a complete A to Z learning path for all serious software engineers. So let's start. So let's start with what is a model really? I mean, when we say this is an AI model, I mean AI model as in Gemini 3, ChatGPT 5.2, Grok. There are multiple AI models that are available. So when engineers say model, they are not talking about a running server, right? A model is simply a data, no logic. A model is a very large collection of numbers. As you can see, the model is nothing but weights, and we have hundreds of thousands of GBs of numbers accumulated, right? And then plus we have some fixed mathematical program, or you can say the logic, the architecture, which uses that weights or numbers to get a output, I mean meaningful output, right? And this is mostly called inferencing. I mean, it's called in the server who is responsible to get meaningful response from this weights, because these are just numbers. It's called inference service or inference engine. Cool. So if we want to build a mental model from what we already know, I mean, if we are able to do a mind map to something that we already understand, let's say we try to map to a simple Java service, or maybe any Java service that you work on your day-to-day life. Cool. So I've created a component mapping. So for any service, we particularly see these four boxes, which is physical infrastructure, execution environment, logic, and basically the executable part of your code. I mean, the part of your architecture, and the model state. I mean, the configs, right? So the code is nothing but a jar or a binary input, a class file, and then we have some data around it, which is the state, config, or DB, cache, any kind of config, right? Runtime, executable time, startup flags, and then we have a runtime execution, which is our JVM for a Java service, and it runs inside a machine which has some CPU and RAM, right? Which is physical infrastructure. Cool. So similarly, as this blue lines gives you, right, the machine, physical infrastructure is the machine, execution environment is our runtime JVM, logic is nothing but our class file or jar files, and the model state are the. So on a similar note, for LLMs, I mean for LLM service, the core logics are something like this. I mean the physical infrastructure is a machine which has some GPU and virtual RAM. Correct? I mean, the code is the transformer inference engine, which is written in C++ and CUDA, the runtime basically. Right? So the runtime execution is in CUDA. We will talk about CUDA and GPU. Why do we need GPU and what is CUDA? I mean, in simple terms, you can say GPU has thousands of little processing unit that work in parallel to accomplish a task. I mean, it's simple parallel processing. So CUDA is, you can assume, as a bridge. I mean, it lets you write code and run it on the GPU. So in simple term, CUDA is a programming plus an execution layer that lets normal code control the GPU directly. Or more formally, CUDA is a platform plus some programming model that lets you run your code on NVIDIA GPUs. Basically, CUDA is developed by NVIDIA. Cool, let's come back. So the logic and the executable, it is the C++ inference engine. We'll talk about inference engine in detail. So for now, just consider it as a black box. I mean, you can consider it inference engine, which actually talks with this model and weights and helps you get the meaningful output. And then the model instead is our weights or tensors, you can say. And I think this gives some basic idea of a mapping. I mean, right? So machine is not machine here. The machine as compared to our CPU RAM, we have GPU and some virtual RAMs, and I mean GPU with large VRAM. I mean, I would say not the simple 8 GB or 16 GB of RAM. So the model itself is not running. The inference engines, the inference engines helps it run, and it loads the model in the memory and talks through it. I mean, it's nothing but the numbers, right? I mean, it's a static values, and this is the, what you can say, a brain of your any LLM service, ChatGPT, Gemini, or anything, Grok. Cool. So let's move forward and see how actually, I mean, what does a model look like on a disk? I mean, we know how a job, when we deploy our binary on any instance, on any machine, we know what kind of directory it follows. I mean, where our actual executable part is residing, I mean, our code file, and where is our config file. So how does a model look like on a disk? So this is a mental model that you can have, which is, it has some model weights. I mean, it is again distributed into fewer chunks, and it has config with some structure, and this is a tokenizer file. I mean, we'll go into in detail like exactly what each thing has a meaning. But the model weights, I mean, the model weights are pure numbers. I mean, mostly floating numbers. And there's no executable code, there's no reasoning, though no business logic, and no if-else statement, just pure number. So on a disk, model is typically a checkpoint directory. I mean, you checked in, which contains some weights, which you get after the training, right? After basically these are the post-training weights that we get, and we divide into multiple charts. And then we have some metadata corresponding to it. We'll talk about what are these metadata and configurations, and mostly the config JSON and the generation config JSON. I mean, along with the tokenizer files. These are pure numbers learned during training, and it's a completely inert. I mean, it itself doesn't do anything until you load it into the memory and then start talking to it and start using those numbers. So there's no logic, no if else, no reasoning code. Simple. Cool. So let's move forward. So now one will ask, Anubhav, then where is the intelligence? I mean, from where we are getting such great output, great response? I mean, if we put in a simple prompt to our models, we really get some crazy output out of it, right? So where is intelligence? So the intelligence comes from how these numbers are used. I mean, how these numbers are influenced. So there's a fixed algorithm called transformer forward pass. So this is a core thing. I mean, transformers are the heart. I mean, that was something that was designed by Google back in 2017, and we'll talk about it. So first, for now, let's focus on the in-memory execution, the inference engine, and we'll talk about exactly from where this intelligence is coming, right? So for simplicity, let's you can simply focus on that the the algorithm which is behind this output generation of prompts is nothing but this is a transformer considered as a function. It we pass the weights. This is the weights. I mean that got. I mean those numbers that we seen right just previous to this. These numbers that got trained. I mean that got out of training data, and then we pass the input token, and then we get the output. It's a very simple algorithm, and that is same for all models because the internal transformers architecture remains same. Only the weight changes. So does the behavior changes. I mean, why why do we have multiple models? I mean, why don't we have a single model? Because every model has a different training data, hence in different weights. So only the weight changes, the algorithm remains same. So if you know the algorithm as a software engineer, that is enough. We really don't care about weights because training this model requires crazy amount of resource. When I say resource, it means machines, GPUs, and crazy amount of money. I mean, for example, training a one billion parameter, or I mean, let's say GPT-3, the training cost was around $10 million. I mean, maybe I'm wrong, but it was something near that. So it's not simple, right? Because it requires a lot of. I mean, we'll also discuss. We will discuss this later. How the actual training happened, for what's pre-training, and then what kind of inference. I mean, how do we inference that thing, and how do we pre-train, post-training, and all the things that are within this cycle. I mean, the training cycle. So this is closer to. I mean, this architecture is closer to a normal CPU. I mean, or you can say a neural CPU, where the program is encoded in form of data, right? So let's go through this diagram. So we discuss the intelligence is nothing but the interaction of data with some maths, and the maths is mostly inside a transformer. There's a lots of matrix multiplication happening inside these transformers, and we learn about each part of the transformer, anyway, each step of the transformer, this position encoding, addition and normalization, feed forward, and multi-head attention. I mean, we'll also learn what is attention, why it is important, and how it is helping us. So yeah, along with this, we have a fixed universal algorithm, which we just discussed, which is this, the transformer algorithm. And then we have a variable learned weight during like post-training. I mean, once the training is completed, we get some weights, which are mostly inert unless it is loaded in the memory and started being used. Cool. So now let's see how this inference engine works. I mean, what is the overview of this? I mean, where does this model run exactly? We'll talk about it later. I mean, okay, we can, it's very simple, right? Where does a model run? A model runs inside a GPU, which has some RAM, and accessed by a long running inferencer. I mean, it is continuously running. And the important details on this is that model weights are loaded only once. I mean, loading takes seconds or maybe minutes. I mean, it's just simply loading the what do you say, static numbers in files, right? And then after that, the model stays there. There's no change in the model unless until you have new model with new training data. I mean, the weights will change, right? So let's focus on the in-memory execution, the inference engine. We'll see how the input token. I mean, this is our input token. Input token as in the prompt that we give to a model is converted into tokens, right? We'll talk about what are these tokens later, but these are nothing but, let's say you pass a sentence, my name is Anubhav, right? So this will be tokenized into numbers or maybe collection of numbers, huge numbers, because our machine understand numbers. And this is processed by a transformer forward pass algorithm that we discussed. On an overview, you can think it as this simple algorithm that we just discussed, which does all the magic and produces an output. But internally, everything is executed on your memory. I mean, this all the maths behind this that we'll discuss later, which is this transform architecture, happens within your GPU, right? It executes the code there and then gets the result. And the model weights are loaded in a disk storage. I mean, it's an encoded program, like simple. I mean, it's model weights on disk, you load it and use it in your transformer powered pass algorithm. Simple. Cool. So the next question, what is actually running on the server? I mean, on a production machine, we typically have this kind of architecture. So we have an operating system, right? We have an operating system. Then we have a GPU driver, CUDA runtime, inference server, which is written in C++. With the help of CUDA, we draw a bridge between our code to GPU. Then we have some model. I mean, the model is loaded in the virtual RAM for faster lookup. I mean, right? It's very obvious. We have loaded on RAM. Then we have a scheduler. We talk about KV caching. It's very important concept. Key value caching here. Then we have a streaming layer, which I mean, when you give a prompt to a model, I mean, any chat service, you get the response in a streaming format, right? You don't get the output all at once. Like mostly 90% of all those applications, we get streaming output. So there's a service that is responsible for that. There's a layer for that. And then we have some sidecars which is responsible for authorization, authentication, logging, and metricing. I mean, all the matrices, info logs, error logs, warning logs. Super. I mean, if you want to compare this with our traditional services, I mean, it would be like we have Java C++ code which goes into the compiler with some CPU instruction. CPU executes the sequential logic, and we get our response. So similarly, inside GPU, the same thing is C++ with some of the CUDA code. We have GPU kernel, a function. Kernels are nothing but functions that are used to run your piece of logic in the GPU. I mean, thousands of GPU threads run in parallel to produce a faster result. Then we'll also talk about the inference server in our next video and how a simple software engineering analogy, how you can compare this. Then we'll also see what kind of phases a model goes through. I mean, the phase one is the training, where you build, which is called the build phase, and then the inference phase, which is the production. I mean, where we actually interact with these models, right? Perfect. So when people say the model answered me this, I mean, I got this response from ChatGPT or Gemini. So what really happens is the inference server executes a transformer. It executes a transformer algorithm on the top of it, and we get the output. Right? This algorithm is ran, and then it's ran against the model weights. It is ran against the model weight on a new input every time, because the prompt always gets changed most of the time, and the model remains same. I mean, the weights are same. It is not getting changed. So during training answers what the model should know, and inference answer is what model says now. I mean, simple training and inferencing part of it. We talk about the inference server in detail.